this is the second type of problem that you can see here, is to determine the penetration into the particular layer to achieve a required capacity. In this case, I think you can see here the required capacity is 30 meganewton. You have a 32 meters of soft to stiff clay with the strength varying from 5 kPa at the top to 200 kPa at the bottom of that layer. So, you can see the strength is varying in this fashion because of a sedimentary deposit, which we discussed earlier on. As the deposition keeps happening, the bottom of the layer, that particular layer, especially the clay type of material, gets consolidated and gets better and better over the years. So, this layer has got a linearly varying. Most of the time you will see clay type of material non-linearly varying, but this particular problem for your easy of solving, just I have given linear. So, 5 kPa at the top and 200 kPa at the bottom, and below which you see a very dense sand. So, with looking at this particular arrangement itself, you can easily see that we want to drive the pile to the better layer, because provision of pile and idea of the deeper foundation, you can see that if you terminate the pile at this clay layer, even at this level, you are not going to achieve any end bearing. So, that you must get it in your mind, because we want better bearing capacity, stronger layer is definitely going to help. Of course, you need to see whether you can just penetrate the minimum required depth, I think, which we discussed about the various cases, 3 cases we saw. So, in this case, whether we want to go for 3 diameter just to achieve end bearing, or you want to go further down to take into account some more skin friction, all depends on what is the strength available from this layer. So, this is a very interesting problem which you will face in real life. So, the idea is, you see here the second layer is a sandy layer. Now, if you remember, recollect the data, sandy layer means the skin friction as well as the end bearing depends on overburden pressure. Overburden pressure depends on the depth to the location. So, unless you assume certain depth and then iterate, you are not going to actually get the answer anywhere. The answer is not straightforward. So, you may have to actually guess probably a first value, quickly do it and then see whether it satisfies. Otherwise, you have to go back, because every time you do not have a x value means you can't find out what is the overburden pressure. If you do not have a overburden pressure, you cannot go and find out the beta times P naught, which is the skin friction, as well NQ times P naught is your the end bearing. So, that is where the difficulty, when you are trying to find out what type of penetration. In many cases, you will find the methodology of generating pile capacity curve, which I described the other day. You divide the layers into several sub layers, find out the capacity, make a relationship between the capacity versus depth. Once you have that, then you can straight away, for example, if you go back to that picture, once you have established such pictures, something like this, once you have established this does not depend on the penetration. This is basically for a given penetration, you can go and find out what is the capacity, or for a given capacity required by the loading, you can find out what is the capacity and the penetration. So, this you can develop without the help of what you need to know is the penetration. What you need is a diameter, definitely you need a diameter. So, every penetration you assume and you calculate and then relate that. So, this graph is very useful, and most of the time this will be available from the geotechnical report, where somebody has come up with borehole information. So, they will give, only problem is only particular diameter may be there, because they will not know what diameter you will come up. So, that is the time you may have to generate more diameters. So, this to generate will take more time in the classroom exercise, for example, in examination type. So, that is why we will not go into here, because to generate this it may require half an hour, 1 hour or even more. So, the best method is to adapt what we were discussing here. That problem is in the wrong place. So, what we want to find out, what is the capacity available? We know very well that once you know the capacity of this pile within the 32 meter, the quantity is known, then the remainder quantity is supposed to be taken from layer 2. So, that is the idea you can find out. So, finding out the capacity of the first layer is very easy, because this alpha method is going to be used. I think I do not have to describe again and again. Only difference here is the strength value is varying from 5 kPa at the top and 200 kPa at the bottom, and you may have several methods to do it. You can actually do what is alpha value at the start, what is alpha value at the bottom, and just use the average value, because only C is varying. Cu varying means psi value will vary, because you have psi is a ratio of Cu by P naught. P naught is also varying. So, the best way is to you divide into sub layers, but for examination point I think if you do at least 3 points or even 2 points, which is okay. You can actually verify when you get time, you divide into several sub layers, you find the answer slightly different, but not excessively different. So, layer 2, you can see here the capacity arising from external skin friction, and the internal skin friction is around 23 to 24 meganewton. What we require is 30 meganewton. So, you are very clear that you are not able to satisfy layer 2 itself, not giving you the required capacity. So, this is layer 1. Layer 2 is a dense sand. So, what we need to do is, now we assume x value and start going by few iterations. First you assume, very well 22 meganewton versus 32 is about 10 meganewton is required. If you have the values of limiting parameters like say beta, as well as the limiting skin friction, and also limiting end bearing is given to in that table will be given, the API table will be given. You can do a quick check how much depth is required in order for us to get the remaining 10 meganewton. Then you can assume a closer value instead of assuming 2 meter, 3 meter, 4 meter. So, the best guess will be very useful, because you can reduce the time required to find the final answer. So, that is how you solve this type of problem, and I think after that it is a similar capacity evaluation, whether it is a plugged case or unplugged case, and then you can finally conclude. Most of the pile will be plugged. So, we will go back to our original sequence of going through the next stage. So far what we have learned is summary is trying to find out the skin friction capacity and end bearing capacity of piles. The principle behind is very similar like our shallow footing, only difference is your stem is having frictional capacity, whereas in terms of shallow footing you only have a bearing pressure at the bottom. So, we have a combined advantage of end bearing as well as skin friction internal external, because you have a tubular pile. Now, all this procedure is well established, and there are several alternative methods. Just now what we have learned is only simple methods prescribed by the codes. If you go into literature, there are other empirical methods or even variation to the methods you will find, but just we need to satisfy the codes and specifications, we need to follow the methods prescribed by the codes. Otherwise, if you actually somebody recommend that these methods are not suitable for the location that you are dealing with, several times that happens in a locality, the codes disclaimer you will read, it will very clearly say that this is only a generic method. In case if you find deviations are required from the codes, you may have to adapt depending on the situation, the experts have to decide. In a similar case, what will happen when you do a design using API, for example even in any known locations, and you actually do a pile testing and you find that the capacity is different from what you have actually arrived based on the codes. So, the decision is not correct, adapting a 100% code method. So, what we will do is we will apply correction factors to either the strength value or to the method itself. Several cases specialist engineers have recommended that we need to modify. So, site specific modifications may be required, which all depends on the engineer involved. So far these methods give you the capacity versus depth for the pile foundation, especially for tubular open ended piles. Now, what we want to find out is the deflection related characteristics. We have decided to give a factor of safety of 2, I think all of you will remember, 2 factor of safety for normalized basically operational roads, or 1.5 for extreme storm conditions. Now, how do we limit ourselves that these factor safeties are going to provide us the required operational condition. For example, I do not want the deflection, vertical deflection, to exceed say 20 mm. That is our original operational requirement for the platform to survive without any excessive deformations. Now, you have no relationship right now to the bearing capacity and the factor of safety and the deflection. So, that is what we are going to derive. Basic idea is how do we relate this. Lot of testing has been done over the several decades of pile installation time, as well pilot testing is done. In fact, before you go for a construction of actual structure, you do the testing first. That means you will construct exactly the same pile as the pile that is part of the permanent structure, which we call it ultimate load test or spare test. You are not going to use that pile, you will just do the construction exactly similar, do the testing. That means you will fail the pile, you will actually go to the ultimate failure stage, and then you will find out whether the characteristics of the load deflection is similar to what you have actually arrived. So, based on that, lot of corrections have been done over the years. Now, what we will see is again what is given in the codes, especially for axial deformation curves. So, let us see what the codes are saying, how the relationship is. As you know very well, if you look at the steel relationship between stress and strain or load and displacement, to certain extent is linear. After that it becomes, if you actually look at tensile test results from your laboratory, you will see very straightforward understanding of linear relationship to certain extent, and then it becomes elastoplastic and then a necking and failure. So, exactly similar people have established, only difference here is tensile testing cannot be done because soil particles are individual. So, you can only do a compression testing, which I think we have described in based on that results you can find out whether what type of deformation it goes through and can come up with relationship. Historically, the notation to understand that axial deformation characteristics is Tz. Z is the vertical displacement, T is the skin friction, which we have used a notation called F. No, so far if you look at the notation for I think F limits, something like this. So, when you achieve the maximum value, then it is denoted as T or T max, sometime we leave it as T. So, when you have friction value is between 0 to T max, if the friction value is in between, pile is not going to get dislocated, because the soil is keeping the pile in the same condition. Once it exceeds the maximum friction value, which is ultimate, once the soil particles get displaced with respect to the pile surface at a particular location, then the pile will start going down. So, you can see the demarcation, it will be having 0 to certain value, the pile will have a minimum displacement, but after once dislocated or the F max is reached, you will see a plastic deformation. So, specifically you can call it elastic, perfectly plastic. After that it just goes through a indefinite deformation. So, this Tz curve, where do we find and how do we relate between the 0 to T max, whether it is straightforward one line or is a curved line. Like if it is like steel, you will expect a straight line, but you may not get, because the behavior is definitely non-linear, and that is where we find the problem of interaction between structure and the soil is slightly complex compared to other analysis. So, you need to do a non-linear response analysis. That means, if you have a displacement of 1 mm for 1 kilonewton, it is not that 10 mm for 10 kilonewton, it is going to be non-linear, it is not a linear proposition. So, that is where we are trying to establish. So, there are two sets of curves, one is for both are vertical, one is the skin friction, which is the side frictional resistance versus displacement, the other one is end bearing versus the same vertical displacement, but at different locations. So, how do we look at, how do we synthesize a pile is you can see here, you can divide the pile into several sub segments of unit length 1 meter, 2 meter, 5 meter, depending on the accuracy required, and each of this pile is denoted by a red color box having a certain stiffness value, modulus, and then moment of inertia, sectional area, and these parameters represent both axial stiffness as well as bending stiffness. So, what you are looking at, each of these pile segment is connected by a soil spring on the sides. Of course, this spring is representing the pile itself, is for axial you can find out EA, the modulus times your axial area. So, the side springs are attached to a rigid datum on little bit far away ground. Imagine if the pile is trying to move, the soil in the vicinity is also trying to get dislocated, but when you go away from the pile, say 2 diameters, 3 diameters, the disturbance of the soil due to the pile load is going to be minimum. I think that is what we saw in our the first analogy of bearing presses. The further you go away, the bearing presses from the foundation load is going to be minimum. Further you go down below the pile tip, also going to be smaller because of the dispersion that is happening. So, you can see here at a slight distance away, little bit distance away, 10% of the diameter, 20% of the diameter, the mobilization of the friction or the strength value from the pile to soil is going to be minimum. So, you can consider that soil as going to be rigid datum. So, the in between soil is trying to behave as a shear failure. So, easy you can understand. So, this spring value, so called the frictional spring, which is what we want to find out. If it is a linear spring like what you see on the first picture, for example, see here, it is a very good linear spring, goes to the maximum value and then it becomes plastic deformation. Whereas, if you see the second spring here, is starting itself is non-linear, means the relationship is not proportional, it is going to be non-proportional to the strength versus displacement, and then has a behavior which is getting degraded and then plastic deformation. So, you can see there are two different ideas proposed and has been tested and then validated. So, you can see here in the sandy layer is linear and then perfectly plastic, in the clay layer is non-linear and then at a certain deformation it becomes lower strength than the strength that you will achieve at a lower displacement and then becomes plastic. So, this is the two shapes which we need is, we need a coordinate points or we need a equation. If you are able to describe this by an equation, then it is good, or if you are able to find out the various points and then you can use them in your calculations. So, ultimately why do we need this when you are doing a system analysis? For example, you want to study the jacket overall behavior of load displacement, you need to describe soil as a spring and transfer the springs into a analysis, because after all every structural element is a spring element. It could be axial spring or it could be a bending spring or it could be torsional spring. So, similar idea, you translate the soil material as a elastic or inelastic material with a spring value, whether it is linear or non-linear. Once you do that, once you do a characterization like this, this becomes part of a structural analysis. So, you do not need to worry about the soil as a separate material, you need to divide and then analyze. So, that is how most of the offshore structures are characterized. You have a structure, you have a soil as engineering material, you transfer the strength properties in terms of spring and then you analyze. So, this becomes part of the structural system. You divide the structure into various subcomponents, each component is attached to the next one. For example, this element it is attached to the previous and the next, and also attached to the side soil value with a certain spring. Once you establish this, then you can carry out the analysis. Most of our structural analysis we go within the linear, so called elastic analysis. So, if you are able to get a spring and if the deformations are within this limit, then this also becomes part of it. A simple static analysis will be able to solve the problem. But once you have this type of non-linear, every time you need to find out what is the structural displacement. For example, in this case, if you go to this, what is the displacement the pile goes through, go back to the soil and correspondingly what is the strength available, and you take it, whether that strength is sufficient enough to transfer the load from the pile. If not enough, then you go for higher deformation and find out what is the strength available and then go back to. So, you do an iterative analysis. So, that is why the pile soil interaction is always going to be iterative, because you are trying to find out what is the strength required in the soil to transfer the load of the pile or the superstructure into the ground with the expected displacement is lesser than or equal to your value. So that's the, so it's an iterative solution. It takes considerable amount of time. That's why many times if you are able to get a linearized thing, then you don't need to worry about it, because it becomes simplified, because you will be using only the one single spring value, whereas here you got multiples of values, because every time you can take a tangent you will get a slope, you will take another tangent you will get another slope. So every time your spring value changes depending on what is your displacement. For example, if initially if you take an initial modulus or initial value of the tangent relationship between the load and displacement, you will get one value. That is how you get your E value. I think if you are remembering stress strain characteristics, the initial modulus is same as the modulus at yield, whereas here if you look at this, every time when you change your tangent value at this point you will get a reduced value, and that's the thing that you are going to do iteration. So the purpose for which we are trying to establish the T-jet relationship is to incorporate this into a load transfer relationship with structure. So just quickly look at how the sand material and what was given by the API. So you can see here 0, of course no strength is available, and at maximum of 0.05 inch. So you can see here this is typically a unit is given, many times it is given in a normalized fashion. In this particular case, old revision of API is giving you this, but of course in the new versions they are trying to normalize this, and maximum value of T max is achieved. That means you calculate your frictional resistance of the soil using P times P naught times beta, which is the maximum value, which is called ultimate skin friction, which we have already learned to calculate. For a given layer you can calculate, that will be the maximum value you can achieve at a displacement of 0.05 inch, which is quite a small value. You can easily understand why. These grain sized particles, so called coarse material, even if you just displace by a little bit, they lose the transfer of forces by contact, because frictional resistance is purely by the contact surfaces, the particle one over the other. Once you displace a little bit, they go disconnected and may not be able to transfer any force. So that is why for sandy material you do not have too much of displacement to achieve maximum resistance. After that it becomes plastic deformation. Once they get dislocated, there is no more load transfer can happen, and that means deformation is very large. So that is why you see the graph something like this, 0 to 0 and then maximum value at 0.01 inch, in fact 0.1 inch, and then it becomes, so basically that is the maximum value, and then after that it becomes almost constant. So that is the type of relationship initially prescribed, but now there are some changes to this which I will share with you tomorrow, because the code is still not in force. They have revised, but yet to announce for implementation, which it will take some time, because this just now the code is in review time. Every company has been given opportunity to give comments. And for clay type of material, you can see here the F value is alpha times Cu, which I think you all know very well. Alpha is related to C and P naught, you can calculate that for a given location, and this F is ultimate, because that is the maximum value after which it is going to fail terribly. So this is assigned as a T max. So you see here is a normalized coordinate system with respect to diameter. So you can see here jut is the displacement, d is the diameter. As the jut by d is increasing, it achieves the maximum value at 0.01, you know. So that is 1% of diameter, isn't it, whereas the other one was actually in terms of inch. So that is the difference that you need to remember. In the new code they have actually normalized to this type of number, which you see a slightly different idea. So in between, in order that if you connect this point and this point, you will get a linear. So in order to make sure that the non-linear relationship is established, or you are able to generate, if you look at the first paper done by Meyerhoff, in fact it was described by equation. The same profile was described by equations of slightly complex in nature, which you will find very difficult to remember. So, API has discretized it, given 4 points. So, you can just use these 4 points to describe. In between you will use a linear, that means from here to here you will straight line, which is reasonably acceptable. You are not going to get something big and then come down. So, that is why the linear between the 2 points is okay. So, if you are able to find out what is the value maximum available for that particular clay, then you come down what is the value of displacement to diameter ratio will happen, and based on that you can use your displacement. This is for soft clay, you must remember, which we need to introduce. What is soft clay? I think we discussed this one few classes back, the difference between soft clay and the hard clay. If you cut a vertical cut, for example, soft clay will try to fall down and come stick with the structure or foundation, whereas the hard clay, what will happen when you cut, it will stay as it is. So, the demobilization of the strength after disturbance is very minimum. For example, you take a pile, you start driving. If it is a soft clay, after disturbance, after several weeks, the soil will come and adhere to the pile system, whereas the hard clay, it may actually stay where it is because of its own characteristics, because it is unable to crumble down and then come back. That is one of the bad characteristics of stiff clay. Even though we call it stiff clay is better for foundation, but for pile foundation is not very good, because you will not be able to get the skin friction back, and that is one of the issue determined by several researchers by doing field testing, and they demarcated that we have to differentiate between the good advantage of soft clay versus the disadvantage of the hard clay or stiff clay we call it. Soft clay, the demarcation is 96 kilopascal. So, if any undrained shear strength is less than 96 kilopascal, then it is called a soft clay, and beyond which we, so approximately you can remember 100 kPa. Now, if you see here the end bearing, so this whatever we saw just now was for skin friction at the sides of the pile. Now, let us move on to the end bearing, which is basically at the tip of the pile. Both sand and clay were given only single relationship. So, you can see here Z by D is a normalized relationship between displacement and diameter up to 20%. Of course, 10% diameter it achieves the maximum capacity. That means you could see one important thing which we discussed in earlier sessions. There is always going to be a problem when you try to share skin friction and end bearing. There is a contradicting statement just now. You can see you drive a pile, in order to achieve a maximum end bearing capacity, the pile should have achieved 10% of its diameter as a vertical displacement. You can easily understand, the more vertical displacement you go through, the soil beneath any loose material is getting compressed, the pile is trying to transfer the load by end bearing. But what will happen when you try to achieve 10% displacement of the pile? All the skin friction is already broken, because you see here, if you look at just for clay and for sand even worse, 1% of maximum displacement, the ultimate strength is reached, and after that it becomes plastic deformation, which is not at all good. So, this is exactly the problem, where when you try to achieve the maximum capacity by end bearing, you will lose all the skin friction, or if you try to achieve full skin friction using only limiting the displacement to 1% of the diameter, you will never ever achieve the end bearing capacity, because end bearing capacity depends on larger pile tip displacement. The more that you compress, especially for concrete type of piles, for example, when you are bored piles, mostly common in onshore structures, you do a boring and remove the soil. I think I have explained you the methodology of installation. Remember, we are pouring bentonite slurry inside to stabilize the soil, and then you replace the bentonite slurry by pumping in concrete. Now, you see here, this process at the tip of the pile will form a very soft layer of concrete, because there will always be debris, you may not have removed it 100%. So, when you completely erect the reinforcement cage, the bottom of the pile will have a soft characteristics. So, as you apply the load, the pile will crumble, basically at the tip it will try to break. Imagine if you take one hard wood and try to poke onto a strong ground, what will happen? The tip will crumble. Exactly that is what will happen to the board pile. The tip of the pile will start crumbling, making a larger displacement. What happens is, once you have a larger displacement, the skin friction is broken. That means you can't take any more skin friction, because the bond between the soil and the concrete is broken. And this is exactly the problem even in terms of steel pile. Once you have a larger pile displacement at the tip, the whole pile is going to go down, skin friction is gone. Lots and lots of debate as well as literature you can find in the articles in several journals, how much you should be taking as a in bearing, when you take how much percentage of skin friction. Lot of published in the literatures. The problem is more for concrete piles than steel piles. API does not actually give you any recommendation that you should limit this much, or you should limit the skin friction. But what it says, when we do the calculation for end bearing for sand, because we know very well that this end bearing in clay is not very good, very small. That is why they are limiting the end bearing to certain value, which we saw some limiting end bearing values. So, as long as you follow the rules given by API, this may not be a major problem. That is why we have to strictly follow the limiting values. So, the end bearing, if you look at the graph, is highly nonlinear, starting to from the starting point itself. You can see here every time it changes. So, this actually was also proposed by not Meyerhoff, another researcher, a continuous equation. It is almost like a parabolic curve, which API has just digitized and given in terms of discrete points, which we will be able to use it for our programming purposes. When you are actually transferring this data to any computer based analysis, so you will require to specify these points. So, what you require is to calculate the T value. The T value for in between is skin friction, and when it becomes maximum will be your ultimate strength. The relationship look something like this. So, it achieves the maximum strength at 10% of the diameter, after which it becomes plastic deformation. Just look at one of the example just to understand. This is for I think is a clay type of material. Undrained shear strength is given as 50 kPa, which is a medium clay, not very soft, not very stiff. Diameter is given. Depth at which this relationship is required is given, 50 meter below seabed, and then you have density of soil is 10 kPa, 10 kilonewton per cubic meter, and you can calculate the P naught value, which is your overburden pressure, height times your density, and since it is a single layer, it is very easy. Imagine if it is several layers are above before the 50 meter, then what you need to do is you need to calculate the effective overburden pressure of those layers plus the layer in question to the point of consideration. So, you have to be little bit careful if you are given a multiple layer question in your analysis, and then you find out the psi value and then alpha value, and then finally find out the f, which is assigned as T max, because that is the ultimate value after which it becomes failure. So, you need to understand the notation, the difference between T max and f. T max is the maximum value of f, which is going to be achieved or mobilized. Now, you know the relationship between the jet and the T max is given in the API graph or the table. So, you can see here the first point is 0 times T by T max was 0. So, you just go back here, T by, in this relationship this is 0. So, the second point is 0.016 and 0.3. So, that is what I wanted to show you. So, you can see here jet by D was 0.016. So, I want to find out what is the value of jet. So, jet multiplied by diameter is given here, and then T max was already calculated. So, I can find out 0.3 times T max will be the T value at that deformation. So, the deformation is 0.0016 times diameter, it could be few millimeters. So, it could be somewhere around 3 millimeter I can say. For 3 millimeter deformation 30% of the maximum shear strength or not shear strength, the frictional strength is achievable. Like this you can develop for all the 8 points or more points if you have the graph, and then put up a relationship. So, you can see here instead of ratio now jet in terms of deflection and basically the skin friction in terms of actual kPa value, you can find out the relationship, and this is what we need to establish. So, the next time if you are given the required skin friction, what will be the corresponding displacement or limiting deflection if you are given, that is the maximum value you can use, not the maximum value that you derive from alpha times Cu, depending on what type what is the deflection. So, this is a typical TZ curve for clay type of material, which I am sure you should be able to derive without any question. The only thing you should remember and note down is multiple layer soils, calculation of alpha depends on the previous layers, the density and the depth and the thicknesses. So, you should be able to do that without any problem. TZ for sand is a similar, only thing is little bit easier because it is only a single and linear point, and the sand is given, overburden pressure is given, and base assign the overburden pressure to the maximum value, and corresponding jet you can fix up is 0.1 inch, and you can see here it is 2.5 millimeter, you get the maximum skin friction. So, that I think gives you an idea. If you go to QZ curve, similar, only this difference is you are going to find out what is the value of end bearing coefficient from the table, because you will be given angle of internal friction, and based on which you can go to the API table and find out what could be the value of limiting end bearing value, what could be the value of the NQ, the end bearing factor, which is in this case is 50, and subsequently you can find out the unit end bearing, which is NQ times P naught, and you find out what is the limiting end bearing value, limit to that value, and then correspondingly in this particular case we try to multiply by end bearing area, so that you can actually plot the displacement versus the end bearing itself, full end bearing, whether it is plugged or unplugged, and then the corresponding points are given. Here it was Z by D versus Q by Q max. Q is the actual value, Q max is the maximum value you will achieve when the displacement is at the 10% level. So, imagine if I decide to do a linear relationship, for example, from here I want to just go up to this point, just I do not want to do a non-linear, whether it is conservative or non-conservative we can decide. For example, if you do that for a given value of 50 millimeter of displacement, if it is a linear relationship you will get a lower capacity, whereas non-linear you are going to get slightly higher capacity. So, does not worry us as long as your assumptions are conservative to the design side. This is because of the convex type of curvature that you are seeing, but what if the non-linear relationship is concave type of relationship, it is like this, then your linear relationship is not very good. So, you have to see the situation, you have to see the difference. For example, in this particular case, let us spend 1 minute. For a 50 millimeter, if I have taken a linear, somewhere here I think it will reach, I will get a capacity of 13125 kilonewton, is not it. Now, if I go to a non-linear graph, I will get somewhere around 25,000. Now, between 13,000 and 25,000 is almost double the capacity. So, should we do a linear or should we do a non-linear? The answer lies in the margin that you want to leave it. You know, basically 50%, do you want to leave it? It may be too much. So, that is why you need not conclude on the basis of simplicity, you should see what is the strength you are losing. Many cases, you know, it may not be like this, only foundation where you are looking at like the linear to non-linear, you get so much extra capacity. In other engineering materials you may not get, you go to non-linear you get only 5%. So, 5% you may think, why do we need to go to non-linear, why not we do a linear relationship, simplify the design process. Whereas here we will not be able to do is because the losing capacity is almost another 100%, which is not going to be very good. So that is why historically we use nonlinear pile soil interaction analysis, because already soil strength is very rare to come by, good soil. So that is why we have to follow this principle.